Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research. From advanced biomedical technologies to breakthroughs in AI, material science, chemistry, and physics, all told as compelling, easy-to-follow stories.
And today we are looking at a really groundbreaking study that was recently published in the journal Science.
Yeah, along with some really detailed research notes from teams at UC Berkeley, the Lawrence Berkeley National Laboratory, and the University of Maryland.
Right, and our mission for this deep dive is basically to figure out how everyday biology is stepping in to solve one of the absolute oldest, hottest problems in heavy metallurgy.
Exactly. But to start off, I actually want you, the listener, to try a really quick visual experiment.
Well, this is a fun one.
Right. So look at the smartphone sitting next to you, or, maybe the laptop you might be listening to this on.
Just imagine holding that sleek, incredibly expensive piece of technology.
Yeah, and suddenly, right before your eyes, the internal wiring just starts turning crumbly and green. Like it literally starts looking exactly like the Statue of Liberty.
Which is, a terrifying image for anyone who just bought a new device.
Oh, absolutely. Heartbreaking.
But scientifically speaking, that is exactly what copper naturally wants to do.
Right.
Left to its own devices, copper just wants to oxidize.
Yeah.
It reacts with the environment and degrades into that really brittle green state.
And, to stop that from happening, engineering has historically had to go to some pretty extreme lengths.
Oh, extreme is an understatement.
Because when we think about the ideal material for modern electronics, we essentially want something straight out of science fiction.
Yeah, we do.
Think of, like, the T-1000 liquid metal in Terminator 2.
Great analogy.
We want a highly conductive metal that we can just easily mold, Something that can flow into any shape or print onto any flexible surface, but that instantly hardens into this invincible, indestructible state.
Right. But physical metallurgy has always kind of treated that idea as an inherent contradiction. Well, you generally just cannot have a material that is highly malleable and easy to process at room temperature while also being incredibly durable and highly conductive. It's usually one or the other.
And so that sets up the central mystery of our deep dive today.
Exactly.
Here's a strange question. Why is it that to make copper, which is, the highly conductive backbone of basically all our modern electronics, survive the real world without corroding, we literally have to bake it at volcanic temperatures?
It's wild when you think about it.
It is. And more importantly, what if you could just, print indestructible copper at the temperature of a hot cup of coffee?
Which, based on traditional manufacturing, printing industrial-grade copper at like 150 degrees Celsius sounds physically impossible.
Right. It sounds like magic.
Yeah, and to understand why people believe that, we really have to look at copper's atomic behavior.
Okay, let's get into it.
So copper is an amazing conductor of electricity. It has superior thermal properties, and crucially for mass manufacturing, it's incredibly abundant on Earth.
Which is why it's in everything.
Exactly.
Yeah.
But it has a fatal flaw. Copper is highly reactive.
It hates the environment, basically.
Yeah, it hates moisture, it hates oxygen, and it hates heat. If you expose raw, untreated copper to the ambient environment, the oxygen atoms just immediately bond with the copper atoms.
And that's when it loses the very electrical conductivity that makes it so valuable in the first place.
Right. It basically turns into a rusty insulator.
Which leads to the current standard industrial fix, right? A process called passivation.
That's passivation.
So to stop our laptops from turning into that green dust we talked about, manufacturers force the copper particles to fuse together into a solid network, and then they coat them in these protective chemicals.
But doing this, it requires absolute brute force.
Like 600 to 900 degrees Celsius brute force.
Yeah, scientists usually have to bake the copper at extreme temperatures just to get it to fuse properly.
And the heat isn't even the hardest part, is it?
Not at all. They do all this baking inside these highly specialized vacuum chambers. And those chambers are filled with forming gases. These are very specific gas mixtures that are designed to purge every single molecule of oxygen from the environment during the baking process.
Because if even a little oxygen slips in at those high temperatures...
Oh, it's over. The copper oxidizes immediately and the whole batch is ruined.
Okay, let's unpack this for a second. Trying to build flexible, wearable electronics using 600-degree copper is basically like needing to weld a metal handle onto a plastic cup without melting the cup.
That is exactly what it's like.
It just doesn't work. The physics completely clash.
Right. Because if someone wants to design, say, a smart shirt that monitors a patient's heart rate, or a flexible polymer screen that rolls up like a newspaper rest.
Which is the holy grail for tech right now.
Exactly. They simply cannot run those soft, flexible materials through a 600-degree industrial furnace. They'd incinerate.
So that extreme heat requirement has essentially become this massive bottleneck for innovation.
It has. Modern technology really demands flexible, wearable, and low-temperature manufacturing.
We want to be able to print circuits directly onto plastics, or thin polymers, or even paper.
But we are largely stuck with stiff, rigid circuit boards, purely because of this high heat requirement to protect the copper.
So industry has basically been trapped in this trade-off.
Yeah, you can have high electrical conductivity and long-term stability, but you entirely lose the ability to process it cheaply and flexibly.
Which brings us to the actual discovery. How did scientists figure this out without melting the cup?
This is where the story gets incredibly interesting.
It really does. So the research paper we are diving into was published in the journal Science on May 14th, 2026.
And it represents a really massive collaborative effort.
Right. Led by researchers Dr. Jun Zhang, Dr. Shenquang Ren, Dr. Heimei Zhang, Dr. Liang Bing Hu, and all their colleagues from UMD, Lawrence Berkeley National Lab, and UC Berkeley.
And what this team created is something they call a reactive copper organic matrix.
Or CuOM for short.
Exactly. They started with a standard copper precursor, which is a compound called copoformate. But instead of relying on that brute force heat and the vacuum chambers we talked about to process it, they introduced a highly surprising cocktail of organic molecules.
I mean, it's wild to see the specific chemicals they chose used in heavy metallurgy.
Oh, completely unexpected.
The organic molecules they mixed in were dopamine, ascorbic acid, and citric acid.
Yeah, let that sink in for a second.
Wait, dopamine, like the chemical that makes me happy when I eat chocolate?
The exact same one.
And ascorbic acid is just vitamin C. We are literally talking about making electronics out of my morning vitamin routine.
Yeah. Now, we usually think of ascorbic acid as a dietary supplement or a biological antioxidant.
Right.
And dopamine is famously the neurotransmitter associated with reward and pleasure in the human brain.
But here, the researchers are essentially weaponizing their chemical properties to manipulate metal.
That dual nature is the key to this entire discovery.
How so?
Well, in a biological system, vitamin C acts as an antioxidant by neutralizing free radicals, right?
Yes.
But in chemistry terms, it is a powerful reducing agent.
Meaning what exactly?
A reducing agent is simply a substance that is very, very eager to give away its electrons.
Ah.
So by mixing these specific biological molecules with the copper formate, they create this totally unique molecular ink.
An ink that prints and actually converts into solid, passivated copper in ambient, everyday air at just 100 to 150 degrees Celsius.
Which is just a fraction of the traditional 600 to 900 degrees.
That is a massive drop in temperature.
Huge. And no vacuum chambers, no specialized forming gases, just a gentle heating process in an open-air environment.
The mechanics of how this works at a molecular level are just fascinating to me.
It's brilliant. Normally, if you try to fuse copper particles in the open air, the oxygen in the room attacks the metal immediately, like we said earlier.
Right, and you get copper oxide,
Yeah.
specifically a type called C2O.
Exactly. And that C2O forms a stubborn physical barrier around the copper particles.
It literally acts like a wall.
Yeah, a wall preventing the copper atoms from touching, fusing, and conducting electricity.
So in a traditional setup, that C2O wall basically ruins the material.
It does. But in this specific molecular ink, the dopamine and the ascorbic acid flip the script entirely.
Okay, this is the part I love.
Because these biological molecules are such aggressive reducing agents, they actually attack that C2O barrier.
They donate their electrons to the copper oxide, stripping the oxygen atoms away.
Exactly. So instead of acting as a barrier, the C2O becomes a temporary bridge.
Wait, so the oxide actually helps here?
It does. The reducing power of the dopamine strips the oxygen away, leaving behind freshly created, pure metallic copper atoms right at the junction points between the larger copper particles.
Oh, wow. So it's essentially generating fresh metal to fill in the microscopic gaps.
Exactly. And what's fascinating here is that more than just filling in the gaps, this specific chemical reduction process is highly exothermic.
Meaning it creates heat.
Yes. The chemical reaction itself releases energy in the form of localized heat.
So as the dopamine reduces the copper oxide, It generates these microscopic, localized bursts of thermal energy exactly where the particles need to fuse.
Right. It provides its own microfurnaces at the atomic level.
That is mind-blowing.
It really is. It accelerates the atomic mobility of the copper without requiring the entire room or the surface it's printed on to be heated to 600 degrees.
And once the copper particles are perfectly fused into a continuous, highly conductive network, what happens to that C2O bridge?
It has been completely consumed. It does
Yeah.
its job as a matchmaker, basically, and then vanishes, leaving a flawless copper wire behind.
It is just an incredibly elegant solution. I mean, the researchers aren't forcing the metal to bend to their will with external industrial heat.
No, not at all.
They are chemically coaxing it to build itself from the inside out.
But that introduces an obvious secondary problem, right?
Right. We have fused the copper at a low temperature in the open air, which is a massive achievement. But how does it survive the real world afterward? I mean, if we aren't baking on those heavy industrial chemical coatings, why doesn't this newly printed copper just rust the second someone takes it outside?
And the answer to that lies in what happens to the dopamine after the copper fuses.
Because it doesn't just evaporate.
No, it doesn't. Under that gentle 150-degree heat, those leftover organic molecules undergo a profound structural transformation called polymerization.
Right, and polymerization is essentially the process where smaller molecules link together to form large, complex, chain-like structures.
Exactly.
A helpful way to visualize this for you listening is to think about baking bread.
Oh, I like this analogy.
Yeah, so when you put dough into an oven, the heat doesn't cause the complex carbohydrates to just vanish.
Right.
The heat causes them to react, link together, and caramelize, forming a hard, impenetrable crust on the outside that protects the soft bread inside.
That is an excellent analogy for what is happening at the nanoscale here.
So the dopamine is essentially forming a crust.
Yes. The carbon rings within the dopamine molecules break open and link together, polymerizing into an ultra-thin, amorphous carbon layer.
Which the researchers refer to as a carbonaceous armor.
Exactly. And the way it forms is crucial. The organic molecules naturally adsorb onto the copper.
And just to clarify for everyone, adsorb with a D is very different from absorb with a B.
Very different.
When a sponge absorbs water, the water soaks all the way through the material. But when something adsorbs, it strictly adheres to the outer surface, creating a microscopic film.
Right, and that surface adhesion is what makes this armor so effective.
It just clings to it.
Yeah. As the copper fuses, the polymerizing dopamine naturally self-assembles into a protective shell around the metal that is only about 3 nanometers thick.
3 nanometers. For context, a single strand of human hair is roughly 80,000 to 100,000 nanometers thick.
So this carbon armor is unfathomably thin.
But despite being so thin, it creates a dense, continuous, graphene-like lattice that completely seals the copper off from oxygen and moisture.
And the data they published on the toughness of this 3 nanometer armor is just staggering.
Let's talk about that data, because imagine leaving a delicate circuit board in an acid bath for a month and a half, and it still works perfectly.
Which sounds impossible.
Right. If you were to drop the motherboard of your current laptop into a bath of harsh industrial acid, the copper wiring would dissolve almost immediately.
Instantly. But the researchers took their low-temperature printed copper and submerged it in harsh acid.
And it survived, remaining fully functional and highly conductive for over 1,000 hours.
Over 1,000 hours. They also subjected it to a highly corrosive sulfide environment.
Like the kind of conditions you might find in heavy industrial plants or deep-sea equipment.
Exactly. And it lasted over 200 hours without degrading.
Wow.
They even baked it in an oven at 140 degrees Celsius for 240 hours.
Yeah.
And the carbon armor held perfectly.
When you contrast that with commercial copper films, the standard passivated copper we use in almost all electronics today, the difference is night and day.
Well, it's not even close.
Because the researchers put commercial copper through the exact same corrosive environments, and it utterly failed.
Right. It completely lost its conductivity in less than 7 hours.
7 hours versus 1,000 hours.
Exactly. You have a material manufactured at a fraction of the traditional temperature, entirely avoiding the need for expensive, energy-intensive vacuum equipment.
And it ends up outlasting the current commercial standard by hundreds, sometimes thousands of hours.
It fundamentally challenges our baseline expectations of how fragile printed electronics are supposed to be.
It really does. The researchers proved that heavy, thick passivation layers aren't necessary if you can just control the chemistry at the nanoscale.
And the self-assembling nature of that graphene-like shield is what bridges the gap from theoretical chemistry to massive real-world applications.
Because they didn't just publish the chemical formulas, right? The
Right.
study details actual working prototypes they built using this molecular ink.
Yeah, the ability to process this ink at 150 degrees allowed the team to literally screen print a highly conductive circuit directly onto a piece of standard flexible paper.
Which is something you could never do with 600-degree copper. The paper would instantly incinerate.
A pile of ash.
Yeah.
But here the paper survives. The copper fuses perfectly. And because the metal is encased in that flexible carbon armor, the paper circuit maintains its high electrical conductivity.
Even when it is physically bent or folded?
Yep, bent, folded, or just left exposed to the ambient air. It still works.
That is incredible. And beyond flexible paper circuits, they also applied this to the renewable energy sector, right?
They did, which is a sector desperately looking for materials that are both cheap and highly durable.
Right, like solar energy is a prime example.
Currently, high-efficiency silicon solar panels rely heavily on silver electrodes.
Because silver is a fantastic conductor and it naturally resists oxidation.
Exactly. But it is a precious metal. It is incredibly expensive, which keeps the manufacturing cost of solar panels artificially high.
And copper is incredibly cheap and abundant, but as we discussed, it normally corrodes, making it useless for solar panels that have to sit out in the weather for 30 years.
Well, until now. The research team used their dopamine-laced molecular ink to print copper electrodes directly onto silicon solar cells.
And how did it perform?
The printed copper performed just as well as the expensive silver electrodes,
Wow.
but with the added benefit of that indestructible 3-nanometer carbon shield protecting it from the elements.
That could be revolutionary for solar costs.
And they took it a step further. They tested the material inside lithium-ion batteries, using the printed copper as current collectors.
And the electrochemical environment inside a battery is incredibly harsh and corrosive.
Very harsh. Yet, over 500 charge and discharge cycles, the printed copper maintained near-perfect capacity, retention, and stability.
It simply refused to degrade.
Exactly.
Refused.
Okay, I do want to temper the hype just a little bit here, just to keep us grounded in the reality of manufacturing timelines.
Fair enough.
Because the idea of printing indestructible electronics on paper is amazing, but we probably aren't going to see flexible smartphones rolling out of our home inkjet printers next week.
No, definitely not next week. You won't be buying a dopamine copper ink cartridge at the local office supply store anytime soon.
Right, that is a really important distinction. This research isn't aimed at consumer-level DIY electronics, at least not in the near future.
So what's the immediate impact?
The immediate revolution here is in scalable, heavy industrial manufacturing.
Right. By completely resolving that long-standing trade-off between electrical conductivity, corrosion resistance, and low-temperature processing, this molecular ink changes the economics of how we build infrastructure.
The real-world deployment will happen in sectors where flexibility and extreme durability are strictly required, but where high-heat manufacturing has traditionally made progress impossible.
So we are talking about things like advanced wearable medical monitors that need to stretch with the human body.
Exactly, or flexible digital displays and next-generation smart energy grids.
Massive manufacturing facilities will eventually be able to ditch their expensive, energy-guzzling vacuum furnaces,
And replace them with low-temperature ambient air printing lines,
which saves a phenomenal amount of electricity and money on the manufacturing side.
making the entire process vastly greener and much more accessible globally,
It really lowers the barrier to entry for producing advanced electronics.
which, is a critical step in modernizing global infrastructure.
All right, distilling all of this down, there are three major takeaways from this deep dive. First, a collaborative team of scientists has successfully invented a molecular ink that takes the manufacturing temperature of copper from a blistering 600 degrees Celsius down to a highly manageable 150 degrees.
And all while operating in normal ambient air.
Right. Second, they achieve this by harnessing the chemical properties of everyday biological molecules.
Specifically dopamine and ascorbic acid. These molecules act as powerful reducing agents that first guide the fusion of the copper and then naturally polymerize into an ultra-thin 3-nanometer carbon armor that seals the metal against corrosion.
And third, this low-temperature, highly durable molecular ink paves the way for a whole new era of indestructible, flexible, and cheap printed electronics.
Proving its viability in everything from wearable tech to replacing expensive silver in solar panels.
Zooming out to the bigger picture, This research offers a pretty profound insight into the future of materials science.
It really does. For over a century, our dominant approach to mastering tough industrial metals has been entirely reliant on brute force.
We mine the metal, we hit it with extreme heat, we lock it in a vacuum.
And we just force it to submit to our engineering needs.
But this study proves that sometimes the most effective way to master a material is through subtle, elegant chemical coaxing.
By deeply understanding the molecular dance between atoms, we can actually use organic molecules to guide the metal exactly where we want it to go.
It's basically the conceptual difference between trying to break a wild horse with force versus simply offering it an apple so it walks into the barn on its own.
That's a perfect way to look at it.
And that leaves us with a truly provocative thought for you to explore on your own.
Think about this. If biological molecules like dopamine, the exact same chemical that fires in our brains to process reward,
If that can essentially teach an industrial metal how to heal, fuse, and protect itself at room temperature,
what other rigid, energy-intensive industrial processes could biology completely rewrite next?
it points toward a very exciting future where biology and heavy industry are no longer viewed as opposites.
Right, but as highly effective partners.
Well, so a huge thank you to you for joining Deep Dive Lab on this journey of discovery today.
Yeah, thank you so much for listening.
If your mind is as blown by the potential of this molecular ink as ours is, be sure to follow and subscribe for more compelling science stories. We will see you on the next Deep Dive.